Hello and welcome back to my YouTube channel. Today I want to take you inside of this Anritsu Step attenuator box and kind of take a closer look on how it is built and what's inside. This specific attenuator, it's labeled MM300032C. Was pulled from a piece of Anritsu test equipment, and I tried to find some specifications or information on the internet. First, I haven't been successful locating anything, so next step was to try to find manual and schematics for the MD80C40A signaling tester this was pulled out of, but unfortunately there are no schematics or any user service information available from Anritsu either. They're kind of tight-lipped about this specific box, probably because it's still a current piece of equipment. It's still sold, and they also obviously want to protect their service organization and service centers, so no information available from this side either. So I took the last step and actually contacted Anritsu service to see if maybe I can get some information from them, but the answer, as expected, came back that it is Anritsu policy not to disclose any technical information about any parts that are used in Anritsu testing equipment. So that's it so far on that one. So, well, we have to basically take to reverse engineer a little bit and figure out this on our own. So generally this box looks pretty straightforward and pretty nicely built. It has a little shield box on top of it, which is aluminum, and then on the sides we have an SMA connector for the RF in and output, and then there's a little header connector right here. Both sides are identical, and then obviously the header connectors are for DC control, and then the SMA RF connectors. There's a base that is gold plated, probably brass or aluminum, and then as we flip this over, there's an aluminum base plate that is screwed down with quite a lot of flathead screws. So it's pretty nicely built. It's not as nicely built as the typical HP step attenuators, which also happen to be smaller in size and more lightweight, or the Anritsu 46 series high frequency step attenuators. But it's pretty well constructed, and so we trying to figure out in this video and the subsequent videos follow up to this one, how this thing is built and what the specifications are. So in this video right now, I'm gonna take you under the hood of this attenuator, show you the insides, and kind of make sense of what's in there. And then the next video, the follow-up, will feature some actual measurements on this box. So the first question, of course, when we look at a step attenuator is whether this is a solid state or a usual old-fashioned mechanical based attenuator. Usually solid state attenuators have become more and more common over the last years in equipment. testing equipment because they offer faster switching speeds, and also obviously because you have no mechanical moving parts, or more reliable in the long term. However, usually solid state based attenuators are not as good in terms of isolation, and also don't offer a performance all the way down to DC or very low frequencies quite often. So first thing try to figure out is what is this kind of attenuator, what concept is used in this box. And so the first thing I'm gonna do is I'm gonna pull off the top cover and see what's under there. Obviously, if it's a solid state attenuator, we would see some additional shielding and MMICs, stuff like this, some control logic. And so I'm going to remove the cover. So I already did this on another unit just to show you. So basically, when we pull the cover off, the first thing we see is those black plastic caps, which are obviously to shield the coils from dust and dirt to come in. So those can be pulled off fairly easy. They're not attached or snapped on or nothing. And then what we see here is basically 2 rows of old-fashioned coils. And those coils, it has this little frame that they actuate and pull up and down. They are not latching, so they have no permanent magnets incorporated in them. So basically they have to be turned on and off by just applying a current to it or turning it off, which is kind of different from the HP attenuators, because the HP attenuators have latching coils, so you only need a short pulse to turn the coil on or off, and which is nice because it's less current consumption, because with those attenuators right here you have to basically keep the coil energized, and depending on how many coils you have in play, you can get quite a bit of current draw on this. So as we can see here on the side, there's no RF related things whatsoever. So the next thing I did is I removed the base plate, and there you go. So now here on the bottom of this, we got a little bit of a better understanding of what's in there and what's going on. So first thing we see is basically up here we have attenuator pads, which are soldered down. You can see the little solder joints down here, and then on the opposite side we have bypass lines, and basically the contacts for those lines are associated with one solenoid each on top of this plate. So basically now we got the RF coming in here. The RF is going on this crossbar right here, and then we have a bypass contact or a attenuation contact coming in that are actuated by the coil. So what that means is basically, if you want to bypass the attenuator, then the coil has to be energized. If you want to put the attenuator in place, since this one is not energized, the other side is energized. So you basically, if you only have one attenuation section in play, you would have to have a total of 8 coils energized. You would have all 7 bypass coils energized and 1 attenuator energized. So there's quite a bit of current draw. I haven't measured yet how much current those coils actually draw, or what voltage they require. But this is basically some part of the second video. So like I said, we got a total of 8 sections right here. 1, 2, 3, 4, 5, 6, 7, 8 attenuator sections. So it depends now, of course, how the sections are organized. We see some of those sections are fairly small value. We can tell this by taking a closer look at the actual attenuation pad sizes. Like, it's kind of hard to see right here. What we see here is it's only one small little black stripe in the middle. That's the actual resistor section. And this one has 2, this one has 2 larger ones, this one's a very narrow one. So basically the narrow ones usually are small attenuation values, and then the bigger ones are larger attenuation values. So that's kind of gives us an idea, but at the end of the day we have to do some measurements on to see values of the pads, and then we can figure out the step size and the total attenuation, what this step attenuator can do. Usually the value of the smallest attenuator pad corresponds to the step size, what you can achieve with the attenuator. And but like I said, since we have no information on it, it's all stuff we got to measure, and we're gonna do this in the next video, where I going to put this on a network analyzer and then use a network analyzer to measure the attenuators. But in order to do this, first thing I have to do is I have to figure out which coil corresponds to which pin on those header connectors. So basically, the way we look at it now is one header connector basically is for the attenuator coils, the other header connector is for the bypass coils, and I have to figure out the pin out, and then kind of rig up a wiring harness and kind of maybe a little switchboard, and then go through it and measure it. So that's it for now. Thank you for watching this video. Thank you for the interest in my channel, and I'm gonna see you in the next video. Have a good day.